This is Unit 3, Moles and Stoichiometry. Lesson 4, Balancing Reactions. How do chemical reactions demonstrate conservation of mass? By the end of this video, you will be able to analyze reactions for conservation of mass and balance chemical reactions using coefficients. Review due now. So conservation of mass is a very important concept for you to understand. In all chemical reactions, there is a conservation of mass, energy, and charge. So make sure you are clear on these three things. Mass, energy, and charge are always conserved. Essentially, what goes in must come out. The number of atoms of each element must be equal on both sides of the equation. Matter and energy cannot be created nor destroyed, only changed from one form to another. So in order for us to balance chemical equations, we're going to use those coefficients. An unbalanced equation does not show conservation of mass. For example, this equation here, H2 plus O2 producing H2O. Here is a particle representation. As you can see, everything in front of my arrow should equal everything after my arrow. I've got two H's here and two H's here, two O's here, but only one here. If we were to talk about masses, if I have 2 grams of hydrogen and 32 grams of oxygen, that does not equal our total 18 grams. So what we must do is balance those equations. Make sure we have the same number of every atom before that goes in is equal to what comes out. So we're going to add a coefficient 2 and add a coefficient 2 in front of these two compounds. So now if I were to take that same concept, now I have 4 hydrogens on this side, 4 hydrogens on that side, 2 times 2 and 2 times 2. I still have 2 oxygens to begin with, but now 2 times 1 is going to make 2. So I have an equal amount of hydrogens and oxygens before and after my arrow. If I were to do that using our masses, 2 times 2 plus 32 is going to equal 2 times 18. So 4 plus 32 is equal to 36. 36 equals 36. So to balance chemical equations, we are only ever going to change the coefficients. We never, ever, ever change the subscripts in a formula. So that's why when I'm balancing this chemical equation, I never changed any of these little numbers. I only added stuff in front, the coefficients. And recall, this coefficient applies to everything after it. So here are the steps. Start with the element that is only found once on both sides of the equation. That makes it simple. Keep our polyatomic ions located on table E together, so we won't break those up if we find them before and after. We can count them as a whole unit if they haven't been broken apart. Coefficients must be the smallest possible whole number. So if they can be reduced, for example, if all of the coefficients in the whole reaction can be divided by 2, we must divide them all by 2. And then check to see that each atom is balanced. So let's try step. N2 plus H2 is going to produce NH3. So the way I like to go about this is I list before how many nitrogens and how many hydrogens I have. I've got 2 and I have 2. So that's in front of my arrow. After my arrow, I like to list them in the same order. I have 1 and I have 3. So you can see right here that they aren't balanced. So in order to balance this one, anytime I see a 2-3 split like this, the best way for me to start is to make both of those equal to 6. Because 2 times 3 is 6, and 3 times 2 is 6. Therefore, both of them will be equal. So for my hydrogens on this side, if I put a 2 in front of my NH3, I'm now going to have 2 nitrogens. So notice when I do the coefficient, I have to change everything after it. Then 2 times 3 is going to make this 6. Then to get my hydrogen equal on this side, I'm going to put a 3 in front. So 3 times 2 is 6. And notice, just by changing that H, I've now balanced the whole equation. Let's try another example. So the way I like to do it, here is my arrow. Draw a line. How many aluminums do I have? How many coppers do I have? And how many chlorines do I have? I have 1, 1, and 2. On this side, I like to list them in the same order. Even though they aren't in the same order, I list them in the same order so it's easy to compare. I have 1 aluminum, 1 copper, and 3 chlorines. So again, whenever I see a 2-3 split like this, I find it easiest to start with that just so that I can get those balanced. So to do that, I have 2. So because I put the 2 in front of the aluminum and the chlorine, I have to update both of these numbers. 2 and 6. Now for my chlorine on this side, I'll do the same thing, 3. So 3, update my copper. 3 times 2 is 6. So now I have my chlorines are equal, but my aluminums and coppers are not equal, but both of those can easily be balanced. If I put a 3 in front of this copper, I now have 3 on both sides, and if I put a 2 in front of this aluminum, I now have 2 on both sides. And now you notice how 2, 3, 3, and 2 are the lowest ratios. I can't divide all of them by the same number and get a smaller value. Let's try one more. I like to draw a line. Before my arrow, I've got a hydrogen, oxygen, 2 of each. After my arrow, I've got hydrogen, oxygen. I've got 2 hydrogens and 1 oxygen. So if I put a 2 in front of my water, so 2 times 2, I have to update everything. 2 times 1 is 2. Now my hydrogens are now no longer balanced, but that can easily be fixed by putting a 2 in front of the hydrogen and making this 4. And those are the steps I follow. Let's try one more example. Oh, it got split. So here is my arrow. I'm going to cross this out, put AgCl up here. That happened when I saved it as a PDF. My apologies. Barium and chlorine. And I'm going to make this a little bit smaller because I have to have 4 things. Barium and chlorine. Silver, and notice NO3. If you look on table E, NO3, you'll find NO3 on table E as a polyatomic ion. So in this case, because I have NO3 on both sides, I'm going to keep it as 1 unit. Therefore, it makes my balancing this equation much simpler. Before my arrow, I've got 1, 2, 1, and 1. The NO3, because it's only listed once, means I only have one group of it. 1, 1, 1. And notice this parentheses with the 2. That tells me I have 2 of these groups. So in this case, I have a couple of things different. If I add a 2 in front of my silver, 2 and 2. Now I have my silver not balanced. If I add a 2, I can change this 2 and this 2, and that balances the equation. So out of my way. Why is this not scrolling? There we go. Types of chemical reactions. So there are 5 different types of chemical reactions you must be familiar with. Synthesis has this general formula. Decomposition has this general formula. Combustion has this general formula. Single replacement has this general formula. And double replacement has this general formula. Notice that synthesis and decomposition are opposites. A plus 2B is going to produce AB2, and AB2 is going to produce A plus 2B. Also, combustion can have any carbon compound as a reactant. So this I can change to anything. What I'm always going to get is carbon dioxide and water. So have these listed. The types of chemical reactions takes a little bit of practice. So for example, a synthesis reaction, 2 reactants forming 1 product. That's our key factor here. Here are 2 reactants, and there's only 1 product. Decomposition is the opposite. I have 1 reactant forming 2 products or more. Combustion, oxygen here, you notice, is always a reactant. The first 6 reactions on table E are considered combustion, and you can use that as your example to remember they always produce carbon dioxide and water. Single replacement reaction is where one substance replaces another. So if you notice, aluminum is by itself here. I have swapped it out for copper here because now aluminum has been combined with my chlorine as a product, and copper is now by itself. A double replacement is when we have 2 substances switching places. So notice how barium and sodium have switched places because in the reactants, barium is with chlorine And as a product, sodium is now with chlorine, and sodium has switched places with barium because as a product, barium is now with sulfate, the SO4, and sodium is now with the chlorine. So check your understanding, and you are now able to analyze reactions for conservation of mass and balance chemical reactions using coefficients.